Welcome to the second section of our second day of the UBC-Tongji CSI Symposium. We had a fantastic day yesterday and a wonderful session this morning. Let's keep up the spirit and continue with the rest of the day, and hopefully we'll have a fantastic banquet. It gives me great pleasure to introduce the session chair of this second morning session, Professor Xiong Haibei, Vice Dean of the Civil Engineering at Tongji University, and myself, Tony Yang. And just to have a reminder for the presenter of this session, if you have an opportunity, please look over to my side, or Professor Xiong's side, to watch out for these two cards. The yellow card representing that you should speed it up your conversation, and the red card kindly stop quickly. Okay? So without any further delay, then we have the opportunity to introduce our first speaker, Professor Xiong Haibei. Please, Professor Xiong.
Okay, thank you for your support the symposium, and that is to be a fantastic symposium. And my presentation today is Introduction to Structural Health Monitoring Systems on the Shanghai Tower. Did that work? So this project is totally by several professors worked in Tongji University. I'm Haibei Xiong, and Qilin Zhang, he's working in large spatial steel structures, and Wei Xinsi, his research is focused on earthquake engineering and base isolation systems, and Aaron Chen, he's working focused on the wind engineering. And the outlines of my presentation includes three parts. The first is background, and then a short introduction to the Shanghai Tower, and then the structural health monitoring system on the Shanghai Tower. The first, more and more super tall buildings are designed and constructed in China or in the world. And they just want to challenge the limitation of the human ambitions, I think, and results and these buildings to be and become a landmarks of the cities and the regions. Here shows some structures completely and under construction will be in these several years in China. And this is the line for the 500 meters. So the more than 500 meters, there are 1, 2, 3, 4, 5. There are also already 5 buildings under construction. And this is the Shanghai Tower. This is the tallest. After it completely, it is the tallest building in China. And this is the 600 meters line. But how about the structure's performance? Is it performed like we design? And if it has some defects, so what will happen? Because there are more than 1,000 people working and live there, so it's a very big problem we should face. And if we found some defects, what can we do? So monitoring on structural responses is then very efficient way to help us to understand the structural performance, and then we hope we can develop the structural performance and improve it to be better. I think this is also a modern solution for seismic mitigation, and this is the topic of this symposium. And Professor Daniel Balaguer, he wrote a book, The Structural Health Monitoring. He gave us a very clearly definition of what is structural health monitoring. So the first step is diagnosis. So diagnosis for the structure is the first. Actually, diagnosis of the structure is the basic information of the structure health monitoring. We got monitoring on the structures, so we can have some responses. And then we use the data analysis and do some research. We can get the performance of the structures. Then we can find some solutions to do and to find some solutions to management the structures. At last, we hope we can design the structures service times. In China, there are some new cases. We just use the health monitoring, structure health monitoring. This is Hangzhou Citizen Hall. There are 5 buildings. There are 6 buildings around together by the ring. So monitoring on the ring and just know that cooperation together is very important issues. And this is Shenzhen Citizen Hall. It's a very large space and with just like a bird flying. And this is Shanghai Expo 2010. And this is steel structures. And this is a very impressive buildings. They, just like this shape. It's Shanghai Voyage Museum. And this is the Sutong Bridge. At first, structural health monitoring started at the on the bridges. So before we just give the monitoring system on the Shanghai Tower, I just want to give some introduction. I think maybe some students maybe will like this one. So Shanghai Tower, it is designed by the architecture design. It's a Gessler Corporation. And the structure design is TT Corporation, Totem Tomacity Corporation. And the local design company is our Tongji Architecture Design Company. The construction time for this building is from 2000. The design and the construction time is from the 2008, and it will be finished at 2014. And what is located here is our venue, and we are just living here. It's the Vancouver UBC, and here is Shanghai. And this at the corner of the river, just like the beautiful river Fraser River here, and this is our Huangpu River. And at this regions, they have 3 very tall buildings. This is the constructed tall buildings, Shanghai Tower, and this is Shanghai Financial Tower. The height is 492, and this is the Jingmao Tower. The height is 420. So there are 3 towers located here in the Lujiazhi rotations. And this is the building. And this is celebration, the milestone toppings of Chinese tallest building. There is 2 weeks before. And the core at the top. And this is Shanghai Financial Center. And the Jingmao Tower just behind of this tower. And the floors is totally is 128. The area, the superstructures area is 380,000 square meters. The underground area is 160,000 square meters. The plot ratio for this building is 12.51. The usage is office, hotel, shopping mall, museum, entertainment. So it is also international buildings. So this is a perspective view. That is just like 2008 Expo torch, and also just like a newspaper, and you join together just like that. And plane just look like this one is triangle, but not line, straight line. It's a curve with some cut. The cut is not only for the unique characteristic, and also can reduce the wind pressure. And this is the architecture design. And for this is the typical plane. We can see that is the outer curtain, and this is inside. They have the inner cores and the mag tubers and the mag columns and the columns. The usage. This is the out curtain, and this is the inner curtain. So inside there have some space for just have some transportation and entertainment. And we like to focus on some structural systems. This is a structural system. So in it, this tube is a concrete with reinforced steel plates concrete. And that also there are 8 mag columns. And then they are connected by the outrigger. And in that some area, they are just surrounded, strengthened by the bale truss. So this is the totally we call this system is mag column, core tube, and outrigger systems. It is common used in super tower buildings. And it showed this kind of structures can give us a very good lateral resistance of the super high-rise buildings. And we can get from this cross-section the mag columns. The size is at the zone 1, it's around 3.7 by 5.3, almost 20 square meters for one column. So this is a column. This is a concrete grate. That is the compression stress is 70 megapascal. And this is the tube. So at the bottom, there's the square. Then just cut the corner, and then they are just slope to the narrow space. And this is the outrigger. So how many outriggers should use in these structures? We also did some research. At last, we just reduced 2 outriggers, and from the 8 to 6. So the outrigger is located here. So the outriggers use the H steel shape beams. The height is 1 meter, and the 6 is 90. So it is a very large plates. The outriggers is through the tube. And that is the floor. The floor is a composite steel and RC slab floor. The thickness is 155, and for the strengthened floor, around 250. And this is a picture for the zone 1, the belt. Look, this is a handsome tall people. This plate height is 1.6 meter, and the thickness is 100 millimeters. So it is another unique for this structure is 2 curtains. And our student, Professor Wensheng Lu's student, will give us a presentation about this kind of the test of the curtains. And that is the crown, the top crown. The top crown is composed of these spatial steel structures. So we just focus on the structural health monitoring. So they include of the earthquake action and the structural vibration and horizontal displacement, because we know for the super tall buildings, horizontal displacement is a very important issue, so we should control. And we also did the wind pressures of the curtain and also wind environment. And we also do some monitoring on the stress and the strain of the key elements, just like the outriggers. And the surface temperature for building. Just we know for these very tall buildings, there's more than 600 meters under the different temperature. The building will be just bending like this or bending like that from the sun, how to say, spray on it. And also, just in the winter and in the summer, the temperature inside and outside different. So we also did some temperature of the buildings and a crack inspect of the key connection point. So we will focus on the earthquake action, the structure, vibrations. I'm sorry, this is some because vibrations. So we use the seismography. We use two seismographies. The first is at the top. The first is at the bottom. The second is at the top. We hope they can always to monitoring the vibrations and recording them. If we have some vibrations, not only by the earthquake, maybe by the heavy truck combined or something, that we can get some of the informations. And this is not sufficient to detect monitoring on the buildings. We also add some the accelerometers. Accelerometers, they are located at the different zone. So sometimes some zones we use the X direction, Y direction, Z, 3 directions, and plus the torsion. So we just put 5 accelerometers at the corner, at the center of the corner, and also at the columns, mag columns. And also in some areas we just put the some just put inside, just in the center of the corner. So totally we put 44 accelerometers in the building. And we also focus on some of the horizontal displacement. We use the clinometer to do the horizontal displacement, because clinometer just use the pendulous type, so he can just always to get the angles from the building, and from these angles we can get the displacement drift, average drift, and then we can get the horizontal displacement. But this building is strengthened by the outriggers, so the shape is not look like this one. This is ideal shape, but this is this kind of building. So where to put the clinometers is also we should research. If we put here and the angle is not so large, if we put here the angle is very large. So how to use the clinometers, and it is also a research topic. That is under the elastic analysis, that is elastic plastic analysis, with under the exceeding properties 2 to 3% the earthquake. So that is the indirectly focus on the horizontal displacement. We also use the GPS for just the double check for the horizontal displacement. So we use several points GPS and to focus on the absolute displacement. So, and for the wind pressures, we use this one to just get the wind speed at the top. I hope we will to let them at the top and just reduce the influence of the another buildings, because it is the topmost, so it's a good position for send this speed meters. And then at the curtain, we also will use some instruments to just get the pressure of this point. So for some located, we will put several meters just to get the pressure. And for this kind of buildings, just we talked before, the structures is composed of the it is composed of the tube, outriggers, and mag columns. So they working together is also important. So we use the outriggers to let them working together. So the elements stress and strain of these elements is very important. If it is larger than we expected, it will result bad things. So put some these stress meters just at the very important element key point. It's important. So we just put some gauges and also this kind of meters just to get the stress and the strain. And after that, we will collect all the data from the different meters and get together it, and to use the Wi-Fi or use the internet by the cable and to get the total information. So we hope we can get the as quick as the data and analysis quickly and to get some results and give the owners what's the health conditions of the building. And this is we design. We hope we can do that because this is the building is under construction, so that is not finished, not yet. So we will. I hope next symposium I can show you some data and analysis. And thank you for your attention. Thank you.
Anybody have any questions for Professor Chung? Such an exciting building. Anybody?
Yes, great question. When you are monitoring for simple displacements, have you been able to verify with the two methods how the displacements compare?
You mean
You said that you were tracking, or you will be tracking the displacements with the GPS and also with an internet, or you'll be able to
parameters? Yeah.
yeah, to calculate the displacements. How do they compare?
Yeah. We think use the climate we can get almost every zone's displacement, and we can get the shape of the buildings. But this is indirectly. If use the not good formulas, and the displacement of the building will be large. It's not correct. So we use the GPS to correct them. But the GPS is not so accurately because they may be just in some 10 millimeters. So we also just use this one to double check. We hope and then we also will use the climate and according to the analysis of finance analysis shapes, and to just double check for this one. And so that is because the experience from our monitoring on the Jingmao Tower. Actually, we do the monitoring on the Jingmao Tower, but because we didn't use the GPS, and we got the displacement under the typhoon, and we showed the data records to the company, SOM company, but they said no, they don't think it's too large displacement, because he just doubt this method is correct. So we just in these buildings we use double systems method to just check the displacement. Thank you.
I have a question about your database. What thought have you put in how you're going to manage all that data? How are you going to process all the data?
Yes, this is a very big question. Actually, we just so several meters that used electric void. We will change that to just like we can use for the displacement. We use millimeters, and we just collect them at the several stations, and we will put this this one, just like displacement, accelerations, and crack, and some wind pressures, and we just compare them with our preliminary design results. If it is large or very smaller than we design, and we will check the results. So the data collection is, I think, it's a large question. I hope next time I can just show you how them come together working. Okay, thank you.
Anybody else?
Okay.
Thank you so much.
Thank you. 下一个是你的是吧？Before Dr. Yang gives the presentation, I just want to thank Tongji Yang, and you give us a very good experience here, and thank you very much. And we also want to thank the Professor Hans Ventura. Although he's not here, but he has some very important business in Denmark, and he also gave us a very wonderful symposium here. Thank you.
Thank you. Thank you.
And I'm glad to be a co-chair of this session.
Thank you. It's a pleasure to have you all here. And we are very honored. Thank you.
Thank you.
Very good. Okay. Fantastic. So I should be looking at this screen. I'll probably just get this off so I don't get distracted. All right. Oh, sorry. Can you hear me? Can you hear me well at the back? Fantastic. Thank you. Good morning. Again, thank you so much for the quick introduction. And it's truly our pleasure on the behalf of all the faculty here at UBC to welcome all our visitors here to our symposium. And we really hope you will enjoy it as much as all the details that we provided for you. Well, I will cut my presentation quickly to the topic. I put myself today in the session about the advanced simulation experimental testing, and the topic for my discussion will be next generation experimental testing methods for earthquake engineering research. Okay, we at UBC take great pride to have the ability to actually working on developing advanced simulation models and experimental testing methods to allow all of us to actually have the ability to understand how the structure behave under severe, significant earthquake shaking or any kind of dynamic loading conditions. One of the advanced experimental testing methods that we are working closely here at UBC will be hybrid simulation. For those of you who have never heard of it before, it's basically an idea of combining computer simulation with experimental testing to understand what's the behavior of the structure system under dynamic load. The right-hand side of this equation could be any loading, static or dynamic. It could be seismic loading, which we do it on a daily basis, or it could be wind, blast, traffic, any kind of loading you're looking for. If you're interested to know more about a hybrid simulation, I highly encourage you to come to the demonstration session tomorrow from 9 to 10:30. We'll have a series of a workshop to show you what's the theory behind it, and we have some small demos for students or other faculty who are not familiar with that to see how the computer works with the laboratory and they all work together. The beauty about hybrid simulation is that we can actually share a lot of resources together, so we can have some component tested here at UBC, another component tested at Tongji University, and another component all the way back to Eco Polytechnic in Quebec City. So this allows us to actually work together much more, and we can actually do a much more complex test and a much more larger scale test. In fact, Patrick, myself, Dennis, we're all working on a big grant. Hopefully, we can all make this laboratory works together shortly. Okay? Very good. The other kind of advanced experiment testing will be shaking table facility. This is one of the pictures that I took last summer when I visited Tongji University. For those of you who have never visited Tongji University, this is the beautiful, amazing laboratories they have there. In fact, it's so amazing. I took my son there, and he told me everything was great. And he was 1.5 years old, and he says, wow, I want to be here. You see,
look at this pacifier. You can see how much he wanted to be there instead of spending time with his mom. Okay. These kind of facilities are built around the world. Okay. This is another testing facility in E-Defense, Miki City, Japan. One of very big facility as well. You can see we basically build a structure system, put on the shaking table, and the idea is very simple. All the ideas are simple. We say we build a structure, put on a shaking table, and see how the structure behaves during the earthquake. So you wanted to have the ability to be actually control the shaking table to re-simulate the amount of energy the table is moving to see how the structure actually behaves. So how do we actually use this for earthquake engineering? Well, this is a picture taken from after the Kobe earthquake where this bridge completely collapsed. If you look at just a portion of this bridge or column, you can put a similar specimen in the laboratory and just like a column with similar kind of reinforcement and the mass is appropriate to that. If you have a specimen like this, it's basically what we always do, a textbook example, a single degree freedom system where you have a long mass on the top and you have the stiffnesses in the structure. And it's actually supported on a big mass, a table, and you shake it and see how the structure actually behaves. Okay? If the specimen is linear, if you have exact measurement of the mass of the table, if it's a brand new facility, yes, you could. You can measure the weight of the table before you actually assemble it. But in some places, if it's old and it's already there, it's difficult to actually estimate that. Other times, if you have an exact measurement of the mass of the specimen, if you have a long mass, then it's probably easy to do. But if you have distributed mass or if you cast your structure on top of the shaking table, then the prediction or estimation of the mass of the structure may not be exact. However, if you have exact measurement of the mass of the table, the specimen, and if the structure behaves linearly, then in theory, you can actually control the specimen to do any way you want it to be. Okay, so to design the controller to control the shaking table, you can think of that's a black box. Design a controller to me is like you all actually doing design control every day. How many of you drove? How many of you can drive a car? Very good. You all are expert controllers, okay? If your car is constantly steering to the left, what will you do? You steer to the right, so you can go straight, right? So that's a very, very basic form of control. So basically, if you look at the whole shaking table and you put it as a black box, I give a signal, I say I wanted to move to the left, and you give me a little bit to the right, I move a lot more to the right, so I actually do what I wanted to do, okay? So that's what we call the basic control, open loop control. But nobody is going to do that and says, okay, if my table is moving, I want to go 1, but it's shooting at 1.1, I'll give a signal about 0.9. What did I do? In my brain, I'm doing the control. I'm saying, okay, I offshoot by 0.1, I undershoot it by 0.1, hopefully I get what I wanted to do. And that's a basic form of control we call it feedback control. So you look into what you give and what you get out, and the difference of then are the arrows. So if I only look at my arrows and say, if I can make sure my arrow is 0, then whatever I give is whatever I get out. So that's actually a very simple way of doing so. However, if your specimen is nonlinear, and if you have any uncertainty about the mass of the table or the mass of the specimen, then the traditional theory about linear control could not work because those controllers are developed for linear system. And for earthquake engineering application, we never test our structure to be linear. We don't even need to test, right? We took it to a highly nonlinear state. The whole thing is spalling, cracking, almost to collapse. So how do we actually pushing this technology to make our testing more accurate and more efficient, okay? And most of the time in the laboratory, you don't have perfect control. You always have disturbance in the lab, you have noises, everything. So all those shaking table control become quite messy, quite difficult. A lot of people just say, nah, it's okay. We just treated those as an experimental error, we live with it. We use whatever signal we recorded from the table, and we go from there on, okay? But the truth is that we don't have to. And that's why we started this a range of nonlinear control algorithms. There are tons and tons of nonlinear control algorithms specifically designed to dealing with a nonlinear system. One of them is called sliding mode control. It's just one of them, and we decided to deal with that first, and we have tons of other nonlinear control algorithms we're going to try. Sliding mode control algorithm was developed by the aerospace engineer to control aeroplane. When the airplane is flying, when the wind blows on it, you don't want your plane to go that way. You want it to be able to control these sudden nonlinear forces to come to your structure, and you can balance your cruise. Okay? So it deals directly with model uncertainties and deal with nonlinearity. So instead of looking about the arrow, I'm looking about the whole system. So instead of minimizing my arrow, I'm going to minimizing the whole state of the structure system. Okay. I'm not going to teach you too much about math, it's too early, but I'm just going to give you a very, very brief idea so you can get out of it and you understand what we are doing. Basically, you're saying that, okay, I can put, it's all came from the Lyapunov stability theory. I think it's Russian. Those Russians think differently than we do. But anyway, they say, okay, if you have a function, as long as this mathematical function is positive definite, so it doesn't matter what you choose for s, the value is always 0 or greater, then a simple example, this will be a positive definite function. Okay? If its time derivative is negative definite, and this is another example that it is negative definite. Doesn't matter what value I choose for s, the function is always less than 0. Okay? So Lyapunov stability theorem just says that if you can find a function which satisfies this criteria, and he proved it, and he's right. If you make a function which is positive definite, its derivative negative definite, what it means is that the value will always go to 0 asymptotically. So s will go to 0 and stay at 0. So what does it mean? Well, for me, if I say, oh, that's a very powerful theory, how do I apply for it? I say, okay, I'm going to make my s as the total arrow between my table velocity and my velocity, both the displacement and velocity arrow of my table. So I add it up. I say, this is the total arrow. I want to minimize it. If I do so, the Lyapunov stability theorem guarantees the arrow goes to 0 asymptotically. If s equal to 0, you can solve this first order ordinary differential equation. It means the arrow goes to 0, exponential decay. So it's not even linear decay. It just goes to 0 and you stay at 0. Okay? So it means my s is 0. That means my arrow goes 0. So I get perfect tracking. So that's a very good idea. Without going to the full theory, proving and all that, let's say I use that and I derive a nonlinear control algorithm. So instead of looking at my arrow at the shaking table input and output, I look at the arrow, I look at the whole system. I started putting sensors in my building, the acceleration in the specimen, all different things I can get it out and come in with the nonlinear signals. Okay? And remember, this particular model deals with uncertainty, so you can make mistakes about your estimate about the mass, stiffness, all kind of things. It will still work. Okay? So we say, okay, that's great. In theory, we can use that theory and apply and develop a nonlinear control algorithm. So we say, okay, let's put it to a test and see how well it does. So basically, in the simulation model, we have 3 kinds of control. Open loop control, I just give a signal and I don't do any correction and see how much it gets out. I do the second one, most people and all the big laboratories doing, we do a feedback control, but it's linear. I give a signal, I look at what's the arrow, the difference between that, I do some correction about it to make sure I get what I wanted. Then I'm going to do the third one, which is do the full-blown nonlinear control, which is using sliding mode control. I do a simulation with the fact hysteresis just assumes to make my mathematical model easy. We did it just one earthquake, doesn't matter which one, but we tried it at the Tibet earthquake. And just to make the simulation a little bit more realistic, I added into additional disturbance, and I also added into the actuator saturation. So you have a machine, actuators in the laboratory. In theory, you can buy better and better actuator. You can ask it to do as fast and as quickly as you want it to do. But in theory, I mean, in practice, our machine could saturate. So I asked it to go to 300 kips, but it could only reach about 240 kips. Okay, so we all include all kind of realistic simulation. This is a very quick movie showing how the structure actually behaves. So you see the animation shows us my structure is moving, going through the earthquake. The simulation is actually modeling the behavior of the structure on the top of the shaking table. You can clearly see that's highly nonlinear. Okay? So this one, we say, okay, now you do an open loop control. You give a signal of earthquake and see how much you get out of it. The red line is how much I want the shaking table to move. because the mass on the top is so heavy, it inserted additional inertial forces to my table, and they're fighting. Okay? So this is ended up to be what happened. The actual table is moving. Most people say, don't worry about it. We are not so certain about earthquake. Just uses the recorded earthquake signal from the table as my simulation and move on from there. So what does it mean to the real specimen? This one shows us the force deformation response about the specimen. The red one is what I want the specimen to actually behave, and the blue one is whatever I do without any doing actual control. So what does it mean? It means is I actually damaged my structure, and I force it to deform 150% more than what you really need to go through from that particular earthquake. Well, if you think about this problem carefully, say, yeah, nobody's going to do an open loop control. At minimum, we're going to do some feedback control. It may not be the best one. Say, absolutely. Okay? So we say, okay, let's move on to the second phase. Let's do some PID control. All the shaking table facility that I know, I mean, probably all of them, is doing some kind of PID control. They have feed-forward, and they have some kind of minor changes to here and there. But the idea is the same. It's a linear controller. It was developed to control a linear system. So basically, they give the signal back and look at the arrow, and you do this disturbance. So to make sure it really works, you can actually design the nonlinear controller by tuning all range of period. You can have a dynamic tuning, all kinds of things. So if you do your things right, okay, if you do your things right, and we tried very hard to make it work, and then we run the simulation of earthquake, this one shows us the arrow of the shaking table displacement. If you look at this and you look at the magnitude of it, you say, wonderful. I mean, this is perfect. If you really know what you're doing with linear PID controller and you do a dynamic tuning where you're changing as a structure, changing period, you can get a very good tracking. Right? So e to the power -3. However, if you go back to look into because this simulation, if you go back and look at how much demand you need the table to be moving, you look at the amount of forces you'll be pushing the table, it looks very jagged, very high frequency, and very large force demand, okay? High frequency, large amplitude. In real life, our actuator could never perform that well. Maybe next 20 years, it's possible. But today, our actuator is saturated. Our palm were not able to make it infinite fast control. So in real life, our actuator saturated in a certain amount. Even I asked you to go 500 kips, it could only reach about 240. It can't go any further, okay? So we say, okay, if you included the saturation into the model, is our PID still doing well? Of course, it's not, right? Because, you ask the structure. I mean, in theory, you can ask the controller to do whatever you want, but it may not really work the way you want it because the hardware constraint. So, okay, then we started going to say, how well our sliding mode control will work using this nonlinear control algorithm. As I say, control is like driving a car, right? Sliding mode control is no different. Instead of looking at your arrow, you started doing fancy driving. You steer your steering wheel, change your gears, and press acceleration and brake at the same time to do some sliding, but you get what you needed to get. Okay? So we actually do that. We ran through the same simulation with the Tabas earthquake, and we're very happy to report it back to you. The nonlinear control algorithm takes into sensors from all these locations and able to track. So this representing the displacement we wanted to go in the shaking table, and in the simulation, it worked very perfectly between the displacement and velocity. Bear in mind the nonlinear control algorithm that I'm choosing, well, I can choose any arrow I wanted, but I'm just saying the arrow of the table, velocity, and displacement should be minimized, and the algorithm will do this nonlinear calculation and send in the signal accordingly, and if your table saturated, it will be able to take care of it. And see, we can see very well tracking. Okay? Now we go back to the input signal requirement for the sliding mode control. So you can see this is way much better than what a PID controller wants us to do. It's much smaller in amplitude because it pre-calculated all this calculation, and it's not such a high frequency signals requirement by the PID control. Okay? And then, obviously, if you control the table properly, you get the response you wanted for your specimen. You say, perfect, that's great. Everything works in theory. How do we actually implement it in practice? Okay? So actually, Wednesday time, depending on the duration of the hybrid simulation morning demonstration. If time permits, I'll ask YJ, he's sitting over the back, to show you how we work on the nonlinear control algorithm, and you can actually go there and see how well it actually performed. Okay, so I asked YJ to actually develop one of these simple single degree freedom linear shaking table. We put huge mass. He was saying that the top of this mass is 100 kilograms. That's way heavier than I am, okay? And it's a small scale model. Basically, you have actuator, you have load cell. At the back of the structure, you have some yielding plates to simulate the nonlinearity. It's in bending. We have a bunch of load cells, accelerometers to actually pick up signals from every location. So we applied this nonlinear control algorithm in real time in the laboratory, obviously. So this is a movie that YJ prepared for me. You can see the structure goes significantly shaking. Oh, it's almost collapsing. Yeah, I'm glad it doesn't collapse and hit my actuator. Thank you. So if you look into the force deformation responses that we generate, the whole thing goes highly nonlinear. I think they caught up before they just stopped. Okay, so it goes highly nonlinear. And we are very, very pleased to inform you that by going back to our results, we make sure the table moves exactly the way we want it. This shows us the table displacement, velocity, and acceleration. And the blue and the red shows us what I want the displacement. The table is working. Overall, this is amazing. The whole thing goes highly nonlinear. We get very good tracking. If you go very, very closely to the zoom in, you can see there's small higher frequency our control algorithm did not account for, because in the derivation of nonlinear control algorithm, I assume it's a single degree freedom system, and some modes may not be included. But we can fine tune about it. But overall, you can get a very good tracking between displacement, velocity, and the acceleration is not as good because it's not into my arrow minimization. So if I wanted, I could actually include some of the arrow of the table acceleration to actually fully optimizes the control. Okay? There are lots of things ahead of us. I mean, we're very excited to report it to you. It's finally working. We have the theory done a while back, and we finally built a table and demonstrated. There are tons of things that we wanted to work with you, including the application of using this nonlinear control algorithm for multiple degree freedom system. Everything you start simple. We did a single degree freedom, unidirectional. We wanted to do multi-degree freedom system. We wanted to do a multi-directional input, and more. Actually, there are really tons of nonlinear control algorithms that we can compare the performance about different control algorithms, and eventually apply it directly to the shaking table facility we have and all of your laboratory as well. Yes, is that red color? I couldn't see it from this angle. But with that, I would like to thank you all for coming to this, and we look forward to have the opportunity in working with you. My last slide is to make acknowledgement to all my students, including YJ, who is sitting at the back, Jason Lin, over here. Yes, thank you, Lisa Tober, Jeremy, and Thomas Duke. Thank you very much for your tremendous amount of hard work to make us look good. Your 25 hours a day working schedule is just working perfectly for me. Thank you so much. Thank you. It's a red card, so the chair can decide if I can answer any question.
It's a fantastic presentation. It gives us a very new idea how to control the arrow. And I think maybe you have some questions. I'd like to give 5 minutes because you're a chair of the symposium. Any questions?
Yeah. Actually, Professor Oliver, I told you it's right here. He checked with me yesterday. He says we should encourage this discussion. So I'll give myself a chance. So if you have any, please talk to me.
I have a question.
Yes.
Can this algorithm or control system be implemented into any existing facility without a big investment? Or
Without big investment? I think so. I mean, I have to look into the particular hardware requirement they have, and also look into the
payload and the specimen they needed to use to check. But in the simulation mode, it doesn't take a lot of upfront investment for us to do a simulation to see. I mean, we simulated all the actuator as well. So we can actually do the simulation to see if this control algorithm works for the application. And then if it works so, it's just from theory into practice, then we just basically slowly changing every simulation portion into real parts. Yeah, I think everything is possible and nothing is difficult. We just have to do it. Yeah.
Yes.
In control the shaking tests, we use control velocity stability. As you showed, you said we can control many other parameters. What are typical parameters we control for a shake table test?
Rohit, your question?
You said we can control based on various parameters for a shake table test. So what are the other parameters in addition to velocity and displacements you would minimize or errors, you would minimize for a shake table test? Typically, is it the force in the actuator? Is it
It's possible, but you're absolutely right. Most
only look at the table performance, nothing more. So most of the time it's some combination of just the arrow displacement of the table, velocity, maybe acceleration of the table, and some combination of it. But in some situation, I mean, this theory doesn't restrict it just on shaking table testing. You can apply to, you basically can make the building dance the way you want it, right? So you can apply to active control to a building if you wanted to, if you have such a technology. So you can say, maybe my performance is not the table movement, it's the top roof drift displacement. Then that becomes what you want to track instead of the table displacement. So you as a user have a choice to decide what parameters that you want to control. So in this example, I say it's most important for my test to make sure the table gives the signals I want it to be. So I look into however possible arrow I can get out. So I look at the arrow velocity, displacement, acceleration. But sometimes you say, maybe that's not important. What I really care was the roof displacement. I want to make sure that we simulated a 30-story building on the top. I wanted to make sure that's what it is moving, what it is. You can use similar algorithm and make sure that's what you're tracking. And the table is doing different things to make sure that's what you wanted.
Sure. Thank you.
Thank you very much.
Thank you. So thank you. Amin. Okay. Very good. Amin is one of our postdoc here. You graduated 2009. Yes. Very good. And if you need it, if your facility need a new faculty, Amin is awesome. Okay. He has been doing a lot of great work with us, and I personally invited him here to show us some of the new high-end simulation capability that we are doing here through the school project. Is that true?
Yes, part of the school.
Perfect. And without any further delay, I'll give you back to your podium.
So actually, this work motivated by the invitation that we got from the Los Angeles Development Association. I tried to put some of our work with this. I mean, for the seismic retrofit program that I'm involved during the last 4 years. But before that, I want to thank Tony for organizing this symposium. So, although the title shows that the efficient performance-based design, I mean, I don't like that efficient at the beginning, but it stuck with that when we submitted our presentation to that seminar. So it's basically performance-based design using the parallel and the cloud computing, which makes it more efficiently for the performance-based design, which requires the more complex models. So I've divided my presentation in two parts. I talk a little bit about what is the cloud computing and what is the parallel computing, and how we can use these new tools in the analysis of the buildings, which you'll see an example at the end, and I'll introduce how these new tools will be incorporated, and we partially incorporated in the seismic retrofit program for the schools. So the advances in the performance-based design and capacity design provides engineers with more direct and rational ways of design. The the Los Angeles Tall Building Association, which they have like an alternative procedure for design of the tall buildings, requires a capacity design in conjunction with the performance-based design. So the design of the tall buildings requires a well-defined kind of 3D models of the structures, which that the inelastic components are well-defined, and the other members should be remain elastic. And performance-based design is used to investigate that the serviceability of the structures for that the more frequent earthquake, like every 40 years or 50 years, and having a very low probability of the collapse for the very rare event, which happens, for example, every 2,500 years. So to investigate the performance of these tall buildings, we need a complex model to estimate that the response of the buildings for the different level of the earthquake, as I mentioned, for the serviceability, and then the estimations of the probability of the collapse. However, as all we know that since when we develop a larger scale 3D complex model for a high-rise building, Tony knows that they are, they are time-consuming. First of all, the modeling is so time-consuming, and running these models, nonlinear time history analysis of these models for the different ground motions, it's very time-consuming, and the data processing requires a lot of time. And as we go through, that's the more complex structural geotechnical problems, like that considering that the soil structure interaction in the bridge problems, for example. So we require more computational power, because in geotechnical problems, we deal with that the 3D finite element modeling of the soil, and then the water pressure. So you have more degrees of freedom. Your mesh is more complex. And compared to that, the structural or the building models, they are more complex, and they need more computational power. So, however, with the advances in the high performance computing tools and using that the multi-core computers, the graphical processors, or the cluster grids and the cloud services, so we can reduce that the time of the analysis dramatically. So especially these days with the parallel and the cloud computing. So I just want to show you what are the available that the high performance computing needs. So perhaps each of you have a laptop, which most of them having the the cores, at least they're double cores, so you should have like at least 4 cores. So, and in universities, you'll see that the cluster, which are the combinations of the different computers which are connected through the local networks, or in more advanced, you can access to the grids. For example, in Canada, we have like the West grid, which I'm not sure as structural engineers we have used it that much, but many faculties around the Canada use these capabilities of these computational capabilities. And actually, the grids is more advanced clusters, which are geographically distributed. So we have clusters in BC, we have clusters in Alberta, so they are connected, and you can log in and then use these computational powers. So recently, like in last 4 or 5 years, the clouds have been developed. So the clouds are actually, that's the similar concept of the grid, but instead of the research or institutional access, so everyone can access to these big and massive computational powers. And actually, clouds provides a web-based IT services to your home. So actually, clouds bring the servers, the applications, the storages into your home. to get the advantage of these powerful computational tools, for sure we should have like that the softwares with that the parallel computing programming. Otherwise, we cannot get the advantage of the multi-cores or the grids or the clouds. So recently, like for example, SAP, they developed like that the SAP Fire, like the engine, which you can assign your modeling analysis to the different processors. However, that the OpenC's, Tony, correct me if I'm wrong, from the beginning it's developed based on that the parallel processing, and some of that the geotechnical softwares like the softwares have these capabilities. Abacus has it, ANSYS has it, and Flags has it. Otherwise, you cannot run Flags without using the multi-core applications. So, what is the cloud computing? Actually, it's goes back to that the 1962. It's not new. So, which the large-scale mainframe computers were being used by NASA for like that for the Mercury project and different projects. So they were basically provided that the physical and access for the engineers to that the physical physical big computer. However, the cloud is that the same concept, but that access to that core and that the big server is provided by that the internet. So if you have your iPhone, or the smartphone, so you can access to the different applications. These applications are brought to you by that the cloud services. So these applications are somewhere in a server, and the access is provided with the high capacity network. So why cloud computing? Because the cost is very low. So you can stop your cloud computing at any time you want. And after finishing your analysis, they are elastic. You can add as many resources, as many clusters you want into your applications. As the size of your building or the modeling increases, you have the visualizations ability, so you can transfer your applications, your development, your files very, very easily by making an image of this and then transferring and assigning it to the different computer, and you can run it and anywhere at any time if you have the internet. The weakness is the internet. So what are the examples? The one of the structural example, which some of you knows, is the NIST hub developed by the network of the earthquake engineering simulation mainly for the research and the education. So you can create an account, log in, and get the advantage of that the cloud platform that provided developed by the Purdue University. And you can access to the different softwares like the OpenSea, SAP, and basically you can run the OpenSeas and using that the parallel computing and then the resources provided there, using that the either OpenSeas SP, which you can run a big geotechnical or a big high-rise model and using the multi-core processing, or you can use the OpenSeas MP, which you can run a big model with the different types of the ground motion. So MP is the multi-processing and the single processor. So the NIST hub is actually it's a cloud platform. The other types are like the Amazon EC2, and there are many commercial cloud services which provides an infrastructure for your development. The NIST hub is basically it's a platform as a service provided for structural analysis and the research. There are cloud infrastructures as a service, so you can rent them, you can access to them, and then develop your own applications. So here at UBC, we are kind of trying to develop a same concept, not the same concept, some applications using that the cloud computing and the parallel processing. So we are trying to develop some structural and the geotechnical applications using that the cloud concept, which that the engineer can access to that the large amount of the resources which provided by the Amazon EC2, or we are trying to find some local ones like that the SAP is in Vancouver, which provides the cloud services, and access to that these large computational powers, and run our applications like that the soil structure interaction, or that's the structural analysis for the school project. So an engineer can access to this web-based application, and they can load their model, and then they can do the live and the direct nonlinear analysis, which takes way faster than the local computers, because they can access to the big sources of the computers, which each of these has like 32 processors, and they can run their analysis on those big computers. So what are the applications? So you can do the sensitivity analysis. 5 minutes? Okay. Sensitivity analysis, incremental dynamic analysis, many types of the applications. So the examples that I want to show is that the nonlinear analysis we did for a 53-story building, which is modeled with which has like a braced core, and also has like a 12 columns, and has the outriggers at each floor, and all these components are nonlinear. So we have selected like we should actually select more ground motions, but for this example, I just selected that the 6 ground motions and run the nonlinear analysis. I use the special case instance in the Amazon EC2, which provides about the 32 process unit, and as you can see, the cost of this renting is very low, and they're getting cheaper and cheaper every day. And actually, these companies motivate you to like do this kind of analysis, and they bring down their expenses. Like with the $3, so you can access to like a 32 processor units. So I ran the Chi-Chi earthquake for this 53-story building, and then you can see that the time of the analysis dropped dramatically, like from 2.6 hours from using one processor to the 0.68. It's about 40 minutes using 10 processors. And as you can see, after a certain amount of the processor, the time of the analysis doesn't decrease because of some sequential procedure in your analysis. So we have a big model, but we are doing the time history analysis, which each step is dependent to the previous step. So we get the advantage of the parallel processing up to 6 processors. So if we have a model with the soil structure interaction, we may get more efficiency using more processor. But in this case, our bottleneck is here. It's using 6 processors. So also, we did the analysis using all those 6 ground motions. So you can see if you use one core, so it takes about 10 hours for you running all those ground motion, which can be done with just in an hour using the 16 processor. You are still using one instant in the cloud, which is like 2.97. It's like about $5 cost. So, and if you want to do the IDA, which we did the IDA, which we have to run the ground motions in the different intensity, so the run times of analysis get down from 78 hours to just 1.5 hours. So and then you can get the different performances of you want, like the floor displacement, the drift, and all these results. And if you have an applications to collect all these data, so you can see them. So another application, as Manuel talked about yesterday, is that the directionality of the ground motion. If you want to run all the ground motion at the different angles, it takes a lot of time, which only just takes about 40 minutes using like all these processors to run all these ground motion at the different the angle. So currently, we are developing this is right now is a standalone software which uses the parallel processing, but we are bringing down these software to the web-based cloud application, which the engineers in BC will use it for the analysis of the concrete shear walls and just some simplified moment frame, which they can get the advantage of the cloud and the computing algorithm, so they can easily define the nonlinear properties for the deflectural, shear, and the rocking, and build up their models. And then, as you can see, that running all those 750 ground motion for the different sources of the sources in Vancouver, like a crustal, subcrustal, and subcrustal, it just takes about 400 seconds, like in less than 6 minutes, which usually takes about 2 hours. They can finish their analysis and get all those probabilities for the displacement drift, and then look at the performances of the structure. So I should stop here. Thank you so much, Tony. Sorry about it.
While the next presenter is setting up, we might have a quick question or two for Amin. Anybody? Yes.
Yeah, I got a quick one for you. Are you using regular software when you go on the cloud with it, or are you using software that's on there?
It depends. These clouds are different types. So, like they call like as a SaaS, which is like a software as a service. So they basically there's a software on the cloud that you are using that software. So some of them are like at the infrastructure as a service. So these clouds provide you an infrastructure, and then you bring your software there. For example, in this case, we brought our software and we develop our software in the cloud, and we use that in the cloud.
Okay, my only concern is that every single piece of that software has a lot of built-in quirks and assumptions. So you get used to one or two of them and make them work. You don't want to keep running into somebody else's.
Well, these services, they said they have like all those safety and other issues. So I don't think we get into those problems later on. Is that your concern? Okay, sure.
To introduce our next speaker, Charlotte Hoffman from the Ministry of Transportation. Yes, Military Transportation of British Columbia. And she will give us a talk about the BC Smart Infrastructure Monitoring System. It's very smart, so please.
I don't know. Which one should I be using here? Yeah, okay. I'm just not sure. Can you hear me with this? I'm sure it's going to go on this pocket somehow.
Very well.
Maybe. Okay. I'm Charlie Huffman. I'm with the Ministry of Transportation and Infrastructure. And we're going to talk today about the BC Smart Infrastructure Monitoring System. And it basically contains two different networks at the moment, which is the Strong Motion Network and Structural Monitoring Network. Where am I pointing this at?
That's if you go left and right, it's going to slide, and if you press, this is really a real pointer. So
No, I don't want to point. Oh,
You just go left and right.
that's what I was doing.
Yeah, it should be working. It's already working up there.
Oh, okay. Oh, I see. It's not working on the computer. Okay. Now I got you. Sorry. Okay. In that case, we'll come over this way. I'm going to speak just briefly about the BC seismicity and the monitoring networks that we have in the province, the BC SIMS, a bit of background on where we're going, and given time, I'll touch on the early warning system for British Columbia. So, we have the pleasure of having two of the three largest tectonic plates on the planet colliding on our doorstep, which means that we go from the San Andreas Fault at the south with our subduction zone up to meet the rest of that north-south slip plane, which we call the Queen Charlotte Fault, on the north end. And in between, we have crustals and various earthquakes in the lower plate and the higher plate, shallow, deep, etc., which makes our situation a little bit complex, and particularly when it gets to early warning systems, it makes it a bit more complex. So the monitoring systems we have are weak motion, strong motion, structural monitoring, and the early warning systems. The weak motion, I guess the important aspects there are it's very sensitive. It is on firm ground, which means that you have to have some geotechnical information where you are, and you have to make a lot of estimations about how fast these waves are getting to you, what's between you and the source, what your ground's made of, etc., to figure out what kind of results you're actually going to have at your site. It requires staff for interpretation, and it clips, as you can see there. The strong motion network, which is obviously my favorite, it's not overwhelmed by strong earthquakes. It does not clip. It is automated. It doesn't need a large staff, which is very handy post-earthquake. It is generally on the surface of the ground or very close, and you don't need to figure out where the source is. You don't care. You don't care what's between you and it. You don't care what the ground is like. All you care about is what you read, where your foundation and your building is, or in my case, our bridge. And they're inexpensive enough that we should be able to densify the network. Not quite how that works, but it should be. This is the Haida Gwaii earthquake, which we had, a 7.7 recently, and you can see the strong motion records there. That top vertical one is actually about twice the scale of the other one, so it should be about half that size. And that's the weak motion record from it as well, and you can see the clipping. This is the Queen Charlotte, which was about the city, which was about as close to the earthquake as we could get with our instruments. When we put our strong motion instruments out, all we need is power and an internet line. We can get the power from a solar panel in some cases if we have to. As far as the internet line goes, we have some creativity there as well. We use cell lines. You can usually use a power cable to jump to a handy spot. But for the most part, we are borrowing somebody's internet line. Well, we don't take up much room. It's okay. This is Powell River, kind of a type of areas that we would put them in. There's the, let's see if this will work here. There it is. This one here is the ambulance station. This is an elementary school, another elementary school, and this is a local airport. As you can see, they're fairly low buildings. We try and minimize the structural interference. The structural monitoring, where we actually want to measure that structural interference, and Professor Zhang was very good about already outlining many of the benefits of that. But we can do damage detection, damage location, which is a bit more complex. And the bonus from the seismic after the seismic point of view is that we get ongoing structural health monitoring, because the instruments don't really care what triggers them. It could be a seismic event, or it could be a ship that kind of missed the pier, or didn't miss the pier, as the case may be. Early warning systems is the other one. Japan obviously is a leader in this, and they've spent many, many years and many, many dollars, yens, and pesos and everything else in getting it working. Turkey has a small but excellent system. Mexico, California have, I would call them limited systems at the moment. BC has an extremely limited system. We have one tunnel with a localized P-wave warning system. But we're getting there. The next step, I think, for many people around the planet is getting that early warning systems up and running, and we're certainly no different, and we're working on ours as well. So the concept of BC SIMS was we wanted something that was instantly accessible, that was available to the general public, to responders. We wanted it automated. We wanted the parameters in public as well as engineering terms, something that we could understand, like intensity, acceleration. We wanted shake maps. We wanted something cheap, low power, all sorts of things. Dr. Ventura can tell you what our wish list was, and it took a while to get to some of it. The team, BC Ministry of Transportation. Sorry, guys, for here I should have probably put UBC first. UBC Earthquake Engineering, who are doing all the heavy lifting on the BC SIMS. The Geological Survey, Research Institute in France, which is INRIA, and supplying some of our really important damage detection algorithms, and our programmers in Denmark. So I guess the question is, why Ministry of Transportation? Because if you look around the world, it's not very often that the people who are supplying your shake maps and running your monitoring systems, or certainly doing their best to drive them, are the Ministry of Transportation. But I guess it started in part because we have very limited resources, and post-earthquake, we have a lot of bridges that we have to inspect. And we wanted to know which ones to go to first, which ones to ignore. Our province wanted to know where the resources were going to be needed. So we needed this information. Following on that and going forward was our realization, in part from some visiting some earthquake sites. China, Chile were a couple of major ones, and realizing just how important the transportation network is. If you want to get your responders in and your equipment in, you need a route in. If you want to evacuate people out, you need a route out. In order to function in there, you need the debris out, which means a route out. To get the building material in, you need a route in. It all comes down in the end to the transportation network. And you can go around a lot of things, but it's really hard to get around a bridge. So that brought us back to our responsibility, not only with the Ministry of Transportation, but also with the bridge group, to keep these routes open and to keep those bridges up. So that gave us sort of motivation and the drive to go forward. So in 2003, when the Geological Survey started sort of a pilot project, as they called it, with Urban Strong Motion, and until about 2005, this is a kind of a map I might get. I get an email saying something had triggered, map to follow, get a map, and it said something triggered. Didn't know how big, how far, and not a whole lot of information on it. In 2006, we supplied some funding and worked with the Geological Survey to at least come up with a GIS mapping. And the ability, when the earthquake triggered, the size of the dot, all the dots are where we have our few instruments, and there weren't very many back then. The bigger the dot, the higher the acceleration, according to this chart, and the darker the color, the more energy. So it gave you an instant intuitive visual of how hard you were hit and where. However, they're what I call static maps, and that means that they don't move. You get this one, you get one that just had this area. We got Vancouver, Richmond on two different pieces. Not the best use of it. So the frustration was wanted it on, and they're sitting on my computer, one in Sydney, Geological Survey, and I think there was one somewhere in Kamloops. So there's very limited people that could see this. So we wanted it on the internet. We wanted to have zoomable maps, and these aren't shake maps. Kind of almost gives you acceleration one, but not good enough. So 2008, we started struggling along, and in 2009, we actually managed to get some funding and go forward to building the BC Sims. By that time, we also knew that we didn't just want a strong motion network on there. We wanted a structural health monitored and seismic for structures network on there as well. So this is what we This is what we ended up with, and I'm not sure you can quite see this here, that the little squares are bridges that are instrumented. The circles are ground instruments. It's zoomable. You get intensity, acceleration. We actually about 3 intensities. Velocity, displacement. We get structural status, and we can put historical events on there. This is a JMA intensity map for a 6.3 earthquake in the Nootka area here. This is where subduction zone comes up, and there's a couple of cross faults in there. It's a very relatively active area. And as you can see, the intensity isn't huge, and it doesn't affect Vancouver. This is actually instrument intensity, a little bit different color, slightly different scales, but you're still getting the same information. When we go into the shake map mode, you'll notice that all of the ground instrument dots disappear, and the only thing that's left is the bridges. That's a little bit because we're involved. We want to know where our instrument bridges are in there. But it also enables us to put other layers on top of there, such as the layer of all of our bridges, so we can see who's in the red zones and who isn't. You can put ambulance, hospitals, health stations on there. You can put water lines, sewage, whatever the user wants to put on there. This is a simulation, and it shows you, though, what being able to zoom in on a shake map can do for you, because obviously this area is okay, and we don't need to worry about our resources there. Our provincial emergency people who are providing responders and funding, they know instantly that this is the scope of the problem they have. They know that this is the area they have to deal with, that downtown Vancouver is probably not going to have a big problem, although they have risk maps and assessments of what kind of damage they have in the area. This is UBC, and they have a really good plan of their own. Probably don't have to worry about them too much. We have a tunnel here, which we probably will have to worry about, because it is going to shut down at not too high an acceleration. So, but we don't have to, we're probably not going to have to worry about any of our structures here. So just the few bridges that are in this area are we going to worry about, and particularly that tunnel. And this is the kind of situational awareness and field intelligence that we need to have. It's also handy for when aftershocks show up, when you're halfway through your inspections. We get system alerts as well. As I said, we can overlay them with bridge layers, the disaster routes, or water or other lines people really want. That's our bridge layer. And as I pointed out, we would only, on that last simulation, have to worry about this particular one and this particular tunnel. Now, I mentioned earlier that the instruments really don't care what triggered them. This is one of our ground instruments on the Sea to Sky Highway, and that's a rockfall, which we picked up kind of nicely. So it doesn't have to be an earthquake to be very useful. So using the BC Sims, we have reports. We give signals to our traffic control center that's in Port Coquitlam area now. We have photos on it, drawings. There's information about the location of the instruments. I guess one of the things that we do with it is all the bridges that are instrumented, we have the 3D finite element models. Yes, they're complex because we want them to be more accurate for the structural health monitoring than you would use for design. And we like to have the soil structure interaction, and I'm really glad to see Armin's got a better way of cutting down some of the work involved in running those. But the system runs constant health runs with it as well. So there's always a comparison and any changes. So aside from being triggered because of the individual instruments or damage or statistical triggering. We also do the finite element runs on them. So it's quite a bit of information that we get with it. Instrumented provincial bridges right now, there's about 12 of them out there. This one is 2 single spans with a reinforced earth chunk in between. So that one's going to be interesting. Other than that, we go from smaller bridges, our tunnel, floating bridge up by Kelowna, larger ones, Second Narrows, Pitt River, Queensboro, and the nice new Port Mann Bridge, which has 400 plus channels on it. We've got a bunch more to come, both existing bridges and new bridges. Various cities, like the city of Vancouver with Cambie Street Bridge, Burrard Street Bridge, which probably gets instrumentation shortly. The Ministry of Education, we have, some of the schools already have ground instruments, but there's also going to be structural health monitoring on an undecided number of the retrofitted ones. Catholic Archdiocese has already identified 20 schools for instrumentation, and they probably go up to about 60, which will all be on the network. This is just some of the information that's on those structural pages. We're right now doing a major graphical interface overhaul with some improved shape maps that should be out very shortly, and mapping for mobile devices a little further down the road, and some messaging and the multi-user data layers. And if I have a couple of seconds here, the early warning system that we're working on is a network system. So we're not just looking at the Cascadia fault and trying to decide how long it's going to take to get to you. What we're looking at is our overall province, and so it's all going to work on a network, and the signals are going to be more alert incoming than an actual number of seconds that you have. We're starting with public schools and Catholic schools, subsidized housing units from our provincial housing authority, ambulance stations, fire halls, that sort of thing, who are very low risk for giving alerts to, while we get all the bugs out of the system over a couple of years, because it's going to take that. If you roll up the doors of the ambulance stations and the fire halls and the earthquake isn't big enough to jam them anyway, well, they don't care because they'll just roll the doors down. And if you don't roll them up and it is big and they get jammed, they'll wish you had. So the kids, well, obviously, duck, cover, and hold. So they either ride out the earthquake or they get a good exercise. So that's where we're at with it. Ministry has provided a lot of enthusiasm and moral support, small amount of funding. UBC has tossed in some funding and a lot of testing, and they have developed actually about 3 or 4 prototype instruments at this point, and we're about ready to go into production on those. They are both weak and strong motion instruments. They got about I think it's a 4 or 6G range that they can manage. They run on minuscule power, and they don't cost too much. Ocean Networks, who runs the offshore underwater instrumentation, they're on board for writing the network software for it. The actual firmware on the instruments itself will probably come from our geological survey friends. That's it. What's your favorite? Here you go.
Anybody has any questions? We have a few seconds going now while we're changing speakers. Thank you for making our traffic safe. Thank you. So, well, very good. So our next speaker is Mr. Oshan. Okay, welcome from Tongji University, giving us a talk about embryon testing, a test on dynamic heuristic of the Shanghai Tower under construction. Thank you. Yeah.
And ladies and gentlemen, good morning. And I'm a student from Tongji University, and my name is Oshan. and my supervisor is Professor Shung. So today, I want to talk about the ambient test on dynamic characteristic for Shanghai Tower under construction. And here are the outlines. The first part is background and goal, and the second part is ambient test on dynamic characteristic. We will introduce this part from 4 aspects: introduction, test scheme, records and data processing, and test the results between 2 different identified methods. And the third part is finite element models. While the assumptions and for the model and the analysis and discussion, we want to make a relationship between the FE models and the analysis and the ambient test. Sorry. And finally, we got the conclusion. As we know, the dynamic characteristic monitoring system of the Shanghai Tower mainly consists of seismic action and acceleration monitoring. For seismic action monitoring, it is a real-time monitoring by deploying by microseismographs in the structure and used for the structure after construction. For acceleration monitoring, it can be divided into 2 parts: the ambient test and the long-term dynamic monitoring. And the long-term dynamic monitoring is used after the construction, and the ambient test is used under the construction. So here is FE models. So we want to make a relationship between the FE models and the ambient test. And that's our goal. The ambient test is applied for getting the load order frequencies and damping ratios of the structure. And the advantage of this ambient test is that there is no need of pre-wiring, which means it will not affect the construction and a short-time data acquisition. And the second one is it can be conducted at any time, according to the construction, design, or other technical requirements. And here are the sensor location and the floor plan. The test is adopted 2 highly sensitive length piezoelectric accelerometers and 4-channel data acquisition equipment and 1 laptop. And the acceleration time history is collected by the SVSA structural vibration signal acquisition and the analysis system, which is designed by Tongji University. To get a more reasonable dynamic characteristic of the structure, each test contains 2 measured points. The measuring point 1 is at the top of the core tube. The measuring point 2 is located at the top compositive slabs of the compression of concrete pouring. According to the sampling theorem, the tested frequency is set to 20 Hertz, and the sampling time is about 45 minutes. Here are the test schemes and the records from the December 2011 to present. In order to understand the dynamic properties of the Shanghai Tower in construction phase, we have totally taken 10 ambient vibration tests and have got several translational model parameters of each construction phase. The date is from December 26, 2011 to July 9, 2013. Here are the steps of the test records. The first one is to set up 2 accelerometers on the top of the core wall, and then set up them on the tallest floor with a composite steel concrete slab. And the third one is the ambient vibration responses in 2 translational directions, X direction and Y direction, have been recorded in each steps. And here are the examples. It's acceleration time history curve. The ambient vibration records in 2 horizontal directions on the 81st floor on October 16th, 2012 are illustrated. A is for X direction and B is for Y direction. And for the estimation of the structural dynamic properties, natural frequencies, damping ratios, it is always recommended the application of at least 2 identification methods with different theoretical background, such as PP method and the double SI method. The picking method with the power bandwidth method and the conveyor-driven stochastic subspace identification technique. So the data processing is identify the PP method, which is in the frequency domain, and the WSI method is in the time domain. Here are the results identified from the PP method. And picking method is a fast and simple technique to estimate the modal frequencies of structure subjected to ambient excitations. And here are the example. Results identified from the PP method in the frequency domain. And the blue one stands for the measurement point 1. And the red line stands for the measurement point 2. And the WSI method is also applied to each selected time series of structural acceleration response in the time domain. Here also an example. It's stabilization diagrams identified from the WSI method in the time domain. So here is a comparison between the WP method and WSI method. We can see for the power spectrum, the high order frequencies get glitches, which may be caused by the interference of the nearby mechanical vibrations. And for the stabilization diagrams, few modal parameters are lost at high order. We can see sorry. We can see here and here. It could result from the identification and spontaneous remove of force mode through WSI method. For these two methods, the low order frequencies identification is clear. So the ambient test results identified from the WSI method and the PP method are proved that the data is valid and available, so it can verify the FE models. So on the contrary, we want to figure out if there is any contributions that FE models can do to the ambient test. So we make a FE models analysis. For the purpose of assessing the ability of the FE models to predict the dynamic characteristic during the construction of Shanghai Tower, a series of three-dimensional linear elastic models corresponding to every ambient test have been developed using the currently software ETAPS based on design drawings. Here, the perspective view. It's Shanghai Tower and the corresponding numerical models at the different construction stages. Here are the assumptions for the modeling. The first one is nodes connected with supercolumns modeled as rigid joints, while the other nodes as hinged ones. The connection between trigger trusses and supercolumn is assumed reliable during the construction stage. This is because the size of supercolumn in zone 1 is 3.7 meters multiplied 5.1 meters, although the dimension of the supercolumns in each zone is gradually reduced. The flexural rigidity of them is still greatly larger than the other components. And the second assumption is for the requirements of design, the elastic modulus of concrete is same to the design value. The third one is structural damping ratio is considered as 1% with the reference of ambient test results. Next, the slabs are set as rigid diaphragms in ETAPS software. This is because no opening exists in the slabs. Considering the slabs construction may at different levels of completion, the establishment of the model cannot exactly satisfy the real requirements. And the second one is no live load which exists in the surface stage is considered except for the top floor of the core tube. This is because there are no occupants exist in construction stages, and the curtain wall has not been hung on the structure yet. And the crane's loading at the top of the core tube is equivalent to its vertical line loading. And the construction load is ignored as it has negligible influence on the dynamic parameters of overall building. Finally, all materials are assumed to perform in the elastic range, and all calculations are based on the elasticity theory. Then we took analysis and discussion, and we take December the 2006-2011 test as an example. Here are the table of natural frequencies comparative analysis. We can see this yellow part and this green part. The identified natural frequencies are correlated with the calculated one, especially for the first and the second modes. We can see this this yellow part of the error is about 15% to 20%, but in the third order frequencies, the average error is about 55% to 60%. So we have got this conclusion. And the second one is first order frequencies average error is about 8.5% to 10%, and second frequency average error is about 7.5 to 9.5%. The third frequency average error is about 17 to 24%. And we counted and merged all the data from the Shanghai Tower every time and the calculated frequencies from the finite element analysis that made this chart. The first two is for the first order frequencies, and the second two is for the second order frequencies. The blue line stands for the calculated frequencies, and the red one stands for the measured frequency, which is identified by the PP method, and the green line is the measured frequencies, which is identified from the SI method. And here are the third order frequencies. So we come to the discussion that the red parts show the data on May the 10th, 2013, had different relationship with others, which reflected the test on that day may be influenced by the ambient mechanical vibration. And the green parts show the third modal frequencies identified from the first two dynamic tests are obviously different from the tendency, which may be caused by the measurement point errors. It's here and here. And the natural frequencies monotonically decrease with the development of the construction, especially for the first two modal frequencies, approximately linearly decreasing. We can see as the story sorry. We can see as the story number is going bigger, the frequency decreasing is nearly like a line. And finally, the identified natural frequency has matched well with the calculated ones, especially for the first and the second orders. And finally, we got the conclusions. Is that the ambient test results identified from the two different identified methods can verify the FE models, and available FE models, on the contrary, can check the test results in the different way. And thanks for your attention. That's all.
Wonderful. It's under time. So you can use the rest of your time for questions if you have any. Does anybody have any question for Ocean? Right. Fantastic. Okay, thank you. So with that, I will introduce the next speaker. Wang Yangli. Yeah, thank you. From Tongji University, about the topic of earthquake actions and testing approach for zonal hanging architecture curtain walls.
Thank you. Good morning, ladies and gentlemen. I'm so glad to be here. My name is Wang Yanling from Tongji University. My instructor is Professor Wen Senru. I'm sorry about change a little about my topic. It's the earthquake action and testing approaches for curtain wall. Because it's time for lunch, so I will speak up my presentation. The outline of my presentation includes the introduction, the earthquake action mechanism of curtain wall, the shaking table test method of curtain wall, and an application of hybrid simulation, and the summary. As envelope system, curtain wall conveys the architecture function and the decoration effects. Attached to the main structure, curtain wall can build the various actions directly with the curtain wall unit and the support system. In the past earthquake, curtain wall have shown vulnerabilities to damages. The damages include the curtain wall union failure, such as the panel breakage and panel fallout. The support system failure, such as the anchor failure and the support structure buckling. The next topic is about the earthquake action mechanism of curtain wall. As it is shown in the picture, curtain wall receives the response actions from the main structure instead of the ground seismic motions. The actions transferred to curtain wall include three direction displacement response and three directions acceleration response. For the main structure response, we can get the acceleration and the displacement response of the floor from the finite element model analysis or shaking table test. It will be used as the input for the analysis of the seismic performance of the curtain wall. The acceleration response of the curtain wall is determined by the input wave and the dynamic property of the curtain wall. So we assume the curtain wall system adjacent between the adjacent floor as a single degree of freedom system. Then the equation of motion is given as follows. The acceleration spectrum response spectrum is used to analyze the acceleration response of a curtain wall. Then we get the enveloping response spectrum from a family of designed input wave. Then it will be modified into smooth design response spectrum, which will be used for the design and test of the curtain wall. As to the displacement response, the displacement transferred to curtain wall is the inter-story relative displacements of the main structure, includes the in-plane displacements and out-of-plane displacements, but only the in-plane relative displacements are discussed. For the stiffness of in-plane for the in-plane stiffness of the curtain wall is much greater than out of the plane. Then the Fourier amplitude spectrum will be used to amplify the displacement response of the curtain wall. The enveloping Fourier spectrum will be get. Then it will be modified to smooth design Fourier spectrum. It will be used to the design and test of the deformation displacements of curtain wall. The shaking table test method have been used to investigate the seismic performance of curtain wall in China, and the recent shaking table test for curtain wall in China were conducted on current Chinese codes. The ground motion was taken as input wave, and the design testing framework was used to simulate the main structure and reproduce the action of main structure to the curtain wall. The codes also prescribe the uniform evaluation index, that is the acceleration amplification factor is 5, which means the peak acceleration value of the curtain wall members should be 5 times larger than the designed peak ground accelerations. And the inter-story drift ratio amplification factor is 3, which means the drift capacity of the curtain wall should be 3 times larger than the limit values of the elastic inter-story drifts of the main structure. Based on the earthquake action mechanism of curtain wall, the recent shaking table tests of curtain wall have some shortcomings. Firstly, the input wave don't reflect many factors such as the dynamic property of main structure, the installation of the curtain wall, and the dynamic property of the curtain wall. And secondly, the testing framework cannot reoccur the required coupled acceleration and displacement actions simultaneously. Then the third is the uniform evaluation index don't consist characters of frequency, content, and the duration of strong motion of input actions. Also, it doesn't provide definite seismic performance level and objectives. So we propose the modified method. It includes the multi-dimensional multimodal hybrid simulation, which is used to recur the coupled multidimensional acceleration and displacement actions on the curtain wall, and the performance-based seismic evaluation method. The principle of this method is that the damage of curtain wall should meet the required performance level under different earthquake levels. 3 types of hybrid simulation are discussed. The first one is multi-node excitation testing method. The devices including shaking table and displacement step-by-step loading devices. The schematic diagram is shown in this picture. This method, the validity and feasibility of this method were verified by the testing of outer skin of Shanghai Tower. I will give some details about this method. Then the second one is real-time multi-mode excitation hybrid simulation. The devices including shaking table and the dynamic actuators. The scheme diagram of this method is shown in this picture. The third one is sub-union hybrid simulation. The curtain wall spacement is divided into experimental and computational substructures in this method. So, about the performance-based seismic evaluation method, the procedures include 3 steps. First one is to confirm the performance objects of the curtain wall based on the seismic classification of main structure. Then the hybrid simulation test will be conducted based on the design smooth spectrum and the evaluation index. Finally, the damage level and the required evaluation index will be checked to evaluate the seismic performance of curtain wall. This table shows the seismic performance objects of curtain wall, which is matching with the seismic classification of main structure. And table 2 shows the performance level of architectural curtain walls. 5 levels were identified. As to the acceleration and the displacement amplification factor, the enveloping value of the input was adopted as the evaluation index. More efforts should be made to obtain the general applied index. Then is the application of hybrid simulation. Shanghai Tower, just Professor Xiong have introduced. The envelope of Shanghai Tower is double skin glass curtain wall. The outer skin glass curtain wall is like a triangle cam in plan. Its supporting system is zonal heating system, and the curtain wall is hand The curtain wall is hanged to the mechanical floor vertically by the red rod, this one, and is connected to the inter-tower by the radial structure, and the rag rod and the radial structure is located at the hoop ringlet. Two types of curtain wall mock-ups are included in our experiment. The size, the panel one is 4,500 millimeter by 1,970 millimeter by 12 millimeter. The panel two is 4,300 millimeter by 1,320 millimeter by 12 millimeter. Then the horizontal and vertical smooth design spectrum was generated. The synthetic acceleron compatible with the design spectrum was used as the input for the shaking table test. And for the displacement input, the step-by-step method was used. As for the vertical relative displacement loading, the internal force of sag rolls was used because the vertical relative displacement was too small to control its accuracy. Table 3 shows the envelope value of the input earthquake actions. It will be used as a seismic performance evaluation index. Then this picture shows the multi-node loading apparatus. It's composing of the main framework, the horizontal displacement loading device, and the internal force loading device. Together with the shaking table, it subjected the specimens into three-direction acceleration actions and the step-by-step horizontal displacements and the internal force. The schematic of this apparatus is shown in this picture. Okay, then I will show you a video about the loading process. In this video, the specimen is subject to real earthquake and the maximum value of horizontal relative displacement and the internal force. Okay, table 4 lists the actual peak acceleration of hoop ringlet and the peak relative displacements. Table 5 shows the peak internal force response of sag rolls. From the table, we can see that the amplitude of excitation for specimen have satisfied the desired intensity in different earthquake level, and all of them met the required index respectively. This picture shows some representative damages in the test. This one is the attrition and the deformation of connection on real earthquake. This one is the deformation rubble gasket on the precautionary earthquake. This one is the relative deformations between adjacent unions. Table 6 lists the seismic performance evaluation of the curtain wall specimens. From this table, we can see that the damage of curtain wall have met the required performance level under different earthquake levels. And so the outer skin curtain wall of Shanghai Tower met the seismic performance objects. Then is the summary. The multidimensional, multimodal coupled earthquake action mechanism of curtain wall is discussed definitely, which will work as the theoretical foundation of the modified. And the hybrid simulation is proposed to reoccur the coupled multidimensional acceleration and displacement actions on curtain wall. And the performance-based seismic evaluation method is developed based on the proposed performance levels and objects. That is all of my presentations. Thank you.
Too polite. Is Professor over here? He encouraged me to at least ask a question from end of every presentation. I guess he's ready for lunch. Well, with that, if no more questions, with that, please join me to thank all the speakers here for the session, and we will go on to lunch shortly after this. Thank you.